So we move on to the second part of abrasive flow finishing process, where we deal with so many things. Till now we have studied abrasive flow finishing process, introduction to abrasive flow finishing. We have studied various elements, that is machine setup, the tooling or fixturing, as well as we have seen the medium. So these are the three main elements of abrasive flow finishing which we have seen, and at the same time material removal mechanism we just touched it about the viscoelastic nature and as well as the abrasive particle, how it will get and other things. So we look into this one from the point of shearing and other things slightly in this particular class also. Then we move on to various types of abrasive flow finishing processes, and the blue ones which in this slide are shows what I am going to talk about in this particular session, and the input parameters and output responses of the abrasive flow finishing process, medium rheology and its effect on finishing, because rheology of the polymer rheological abrasive medium is the main thing that one has to understand if at all a person want to work in abrasive flow finishing process. Okay. So the advantages and applications of abrasive flow finishing process that we will see. Apart from it, we just see some of the material removal mechanisms also in this particular class. Okay, this is what we have seen, the abrasive flow finishing process, where the setup is there as well as tooling and medium are the three main elements of the abrasive flow finishing process, and we move on so that the finishing will take place in the shearing zone. So the material removal mechanism in the previous class I could able to explain you, but from the forces point of view and others point of view I would like to explain here. If you see, the extrusion pressure is applied. If you are going to apply the extrusion pressure, in the previous class we have seen the downwards arrow, in this one you have a upward arrow, or if you assume that you are going to apply the extrusion pressure in the same direction, if you take here, so there are radial force and radial velocity. Radial velocity is neglected because indentation velocity is negligible compared to axial velocity. Okay. So this is axial velocity and axial force and radial force. So because of the radial force, this abrasive particle will try to indent on the surface, and because of the axial force and velocity it will try to move in this particular direction. Okay. This is FR and this is FA and VA, and this is FR, so that the chips will be generated and these chips will accumulate in the medium. How it will accumulate and all those things we will see. This is the mechanism that we have seen, and which we have not seen in the previous class is how the abrasive particle, this particular abrasive particle is going to get the assistance of viscoelastic nature. So the viscoelastic nature is explained in the previous class. The schematic is given again here. So whenever you have a extrusion pressure, the viscoelastic element, viscous component tries to move in this direction. This is the direction of applied pressure, and elastic component moves into perpendicular direction. Because of these two, the material removal will take place. This viscous and elastic effect will support the abrasive particle. That is what we are seeing in the above picture. So the viscous and elastic components, that is axial force and axial velocity, will move in this direction, and radial force will move in this direction. Because of the radial force, the indentation takes place, and because of the axial force, what will happen? These particular peaks will be sheared. Okay. So you will get the surface finish. That is what the material removal mechanism and how the viscoelastic effect came into picture. The viscoelastic nature of the medium is not that much easy to identify. So once the researchers started their career with so many polymers and other things, but once they know the mechanism of viscoelasticity and other things, then only you could able to make the medium in a perfect way, because we need viscous effect as well as elastic effect. How the viscous effect is going to help the abrasive particle, how the elastic effect is going to help the abrasive particle. These signs should be understood before proceeding towards the abrasive flow finishing mechanism. If you see the material removal mechanism in this particular process, so initially we have the grinding surface. Assume that this particular surface is the aluminum alloy and silicon carbide metal matrix composite. This is the initial surface roughness where you are going to see the initial grinding marks. These are the grinding marks which you can call as a lay. This is called lay, that is nothing but predominant direction of surface roughness in a grinding operation. So after 100 number of cycles, because always you place your workpiece perpendicular to the medium flow direction. Okay, so what you have seen, this is your fixture and this is your workpiece, and you are placing them again the fixture and you are reciprocating. So what will happen here is, whenever you reciprocate the medium, the medium flow direction will be like this. So always you place the grinding marks perpendicular to it. So that means that your workpiece, if I adjust for example understanding purpose, the grinding mark should be like this. On top of it, the abrasive flow finishing medium will reciprocates like this, so that you can see the dominating the marks of grinding process here, and there will be small abrasion or the micro nano scratches also you can see on this surface in this direction. These directions are abrasive flow finishing directions, and these directions are grinding directions. Okay, so this is how the finishing starts, or shearing of the surface peaks that are generated by the grinding process will be sheared. If you go on increase the number of cycles by keeping the extrusion pressure and medium composition constant, you are dominating shearing marks of the abrasive flow finishing process will gradually increase, and your grinding process lay directions, which are small they will goes off. So dominating ones only will be staying. Okay, so as you increase number of cycles, what will happen is surface lay that is generated in the grinding will goes off gradually, and at last you will get a fully fledged abrasive finishing processes, and you will get a very better surface on this one. And if you see 400 number of cycles, then you are going to get a very good surface marks of abrasive flow finishing process, and you may not find many of the grinding marks, and you may find two dominating scratch marks of the grinding process. Okay, so that's how in 400 cycles, where it is a laboratory setup, the medium flow is approximately, you can say it is 200 to 250 grams is the maximum medium that you can place in a medium cylinders. Okay, so in a commercially way, what is people will do, they will going to put few kgs also. In that way, the number of cycles you are going to experience the surface finish will be very few. So don't go by number of cycles many times. This is always depend on what is your medium cylinder capability. If your medium cylinder capability is too small, your number of cycles will go up. If your number of cycles will go up, what will happen is your medium gains some temperature because of shearing action at faster rates. So that's all. Some of the problems will be there in a laboratory scale. However, this laboratory scale things that we have used in this particular experiment are economic to produce. That's why this is done at the laboratory scale itself. Okay, this is how you can see that completely grinding marks are transformed into finishing marks of abrasive flow finishing process. Okay, this is how the material removal mechanism will takes place, and whatever the physics that I spoke in the previous slide about the viscoelastic nature will shear the surface peaks of the grinding marks gradually disappears, and only abrasive flow finishing marks will be appearing on the surface. So, in the previous slide also you have seen where these particles will go or where these chips will go. As I discussed in the previous class, these chips will embed into the medium and this medium slowly gains the bluntness of abrasive grains, as well as this will gain number of chips into it. This number of chips as increases, the weight of the medium goes up. Once the medium's weight gains to 10% of its own weight, that means that 1 kg, that means 1000 grams, if you are going to measure your weight after few experiments, if it is 1100 grams, then you have to discard the medium. So, you can clearly see the chips of different sizes, these different sizes because of your shearing nature. So, some of the abrasive particles may agglomerate and shear, so you will get a big chip. If you are going to have a one abrasive grain is shearing, you may get a small chip and all those things. Mechanism is completely random because your particle location is random and particle shape is random, and many randomness are there because it is a two-phase medium and it has to remove by the virtue of polymer A, polymer B, many things are there because that medium compositions and all those things we will see in the next slides. So, the classification of abrasive flow finishing process, there are normally 3 varieties. One is unidirectional flow abrasive flow finishing process, two-way abrasive flow finishing process and orbital abrasive flow finishing process. Unidirectional abrasive flow finishing process also called as one-way abrasive flow finishing process also. Okay. First we will see unidirectional abrasive flow finishing process where the medium is located in a medium collector. This one, this is the location and this is pressurized by using a hydraulic cylinder and piston, and the medium will pass through the extrusion medium chamber, extrude through the workpiece. Okay. You can see the workpiece is there and it will extrude into this area and this will come, there will be a lid which will open and this will enter into the medium cylinder whenever the piston goes towards upside. Okay. This is how it will be recycled. So, medium will be placed in the medium chamber and abrasives and medium are extruded through the workpiece to be finished. This is called one-way abrasive flow finishing process. As you can see here, one-way abrasive flow finishing process pushes the abrasive media through the workpiece only one direction. That is why, because it is pushing in only one direction. Okay. Whenever it is pushing in only one direction, this is called one-way abrasive flow finishing process or unidirectional finishing process. It is not pushing whenever it is retracing the path towards backside. Okay. It is just goes because of to allow the medium that is extruded from the workpiece to comes into medium collector. Okay. So, the workpieces that are finished by using this particular process are like engine blocks. So, whenever you have this type of blocks which are complicated to finish, then you just connect this with a proper tooling and then you just try to finish. Okay. You can see here unfinished one and you can see the finished one here. At the same time, you can finish any type of complex surfaces using the one-way abrasive flow finishing process or unidirectional finishing process. So, the another application of this particular process is you do not require the medium collector and other things, that is called the multiple holes based workpieces can be finished. Multiple holes based workpieces where you will have a big medium cylinder wherein the medium is filled and you are extruding through these holes. Whenever you try to extrude this one, what will happen? It is a one way. So, the medium comes out through these holes and these holes will be finished properly and the medium will be collected using some external source and then it can be reused again and again for similar type of workpieces. Only thing that you have to note in this particular picture is that there is no automatic medium collection unit here. Only thing is that once it is pushed or extruded through the holes, this medium comes out and the external people or external system will collect this medium and they will be using for again manually placing this particular medium inside the medium cylinder. Advantage of this particular process is faster cycle processing and easy to clean up because this is external. So, any unexperienced person also can collect. There is no need of highly expertized person whose payment will be very high. So, normal persons can easily clean up. Medium temperature control generally not required because here in one go the medium is coming out. So, there won't be requirement of any temperature controlling unit. As I said, if you are going for many times of reciprocation, as you have seen the basic type of abrasive flow finishing process, that is called two-way abrasive flow finishing process, that you have seen in the previous lecture, where the medium is reciprocated in a two-way. So, that we will see in the next slide. So, in that circumstances, what will happen, the medium has to go through the narrow region of workpiece. Whenever it is going through a narrow region of the workpiece, the temperature rises because of the friction that is experienced by the medium. So, you require to control the temperature. For that purpose, you always go for temperature controlling unit. So, able to process larger parts, it does not matter whether it is a small part or a big part. If this is a very big part, whatever you are seeing in this picture, and this can be accomplished in a one go. So, simpler tooling and part changing over, that is required because here simple tooling is required because you are extruding from one direction and the finishing is taking place in a straight away. So, accurate and replicate air, liquid, natural flows, and it does not encapsulate work part in the medium. These are the advantages of one-way abrasive flow finishing process, and then we move on to the two-way abrasive flow finishing process, which is commonly used for explaining the physics of the abrasive flow finishing process. So, that is what we have seen in the previous class. Whenever I talk about abrasive flow finishing process, normally to make the science and the physics easy, we understand, or by default we take two-way abrasive flow finishing process. This is a process that we have seen in the previous class. However, we will see two-way abrasive flow finishing process uses two vertically opposite cylinders that extrude the abrasive media back and forth. That means that this abrasive medium is reciprocated back and forth. Abrasive action occurs when the media enters and passes through the most restrictive passage. That means that if you see in this picture, the most restrictive passage is this particular thing. So, this particular part is the most restrictive region, because of which the medium experiences more restriction. So, that means that the abrasives will abrade more in that particular area. The common type of workpieces that will be finished by using this one is through holes type of things. Okay. In the previous case, you can go for through holes in a wall or some other places. If at all I have a dies like extrusion dies like this or like this, what is happening is these extrusion dies can be placed in the workpiece region and this can be finished in a straight away. So, the medium will try to reciprocate through this one and this will be finished. So, deburring action also can be taken place by using abrasive flow finishing. So, the advantages is excellent process control will be there, can finish both internal diameter as well as outer diameter. This will be depend on how you are going to develop the tooling for the workpiece material, and good control of radius generation is there, and fully automated system capabilities can be done. and fast setup and quick change tooling and fast stage changeover of the medium and other things will be taken. So, this type of deburring also can be done by the abrasive flow finishing process. However, this deburring also can be done by thermal based deburring process also. Okay. So, for that purpose, if at all one has to go for this type of deburring process, what you have to do is you have to have proper tooling. Okay. So, the bottom one can be finished by abrasive flow finishing process. However, the top one normally people prefer thermal oriented finishing processes for the deburring applications, and you have every chance to use the abrasive flow finishing process also if you can maintain the proper tooling. So, the third variety of abrasive flow finishing process is orbital abrasive flow finishing process. The orbital abrasive flow finishing process normally uses for the blind holes type of workpieces. Okay. So, for example, what you are going to see here is the medium is there and this is the workpiece and this is the tool basically. So, the medium will reciprocate in the vicinity of or in between tooling and workpiece. So, you can see here this is the medium piston that is pushing here and another piston is here. So, piston 2, piston 1 is there. So, this piston 2 and piston 1 tries to reciprocate the medium. So, the orbital motion is given to the tooling. If you are going to give this type of things, what will happen is whenever due to the orbital motion of the tool, the medium will get the narrow, the medium will try to finish the shape that is there in the workpiece region. That is how the medium will help in finishing the blind holes. Normally finishing the blind holes is one of the difficult tasks. You see, if you see the mechanism of orbital abrasive flow finishing process, workpiece is made to oscillate in 2 to 3 dimensional planes with a slow flowing stream of abrasive flow finishing media. Then opposite to the flowing media, work part is stationary and dispenser, and as the elastic abrasive medium flows between the two surfaces act as continuous and self-sharpening and fully forming polishing tool. The small amplitude oscillations, normally typically 0.5 to 5 mm in conjunction with the ultra-fine abrasive particle media, deliver high uniform microfinish on any complex geometry work part material. Okay. Normally tool is made to oscillate or given orbital motion. Then the workpiece is stationary, in between the medium will try to reciprocate, and because of these multiple actions of the tool as well as the abrasive medium, the workpiece will be finished into micro to nano level. So, the simple to complex surfaces that one can finish using orbital abrasive flow finishing process is this. So, you can finish this type of dies which are given, at the same time coins also you can do the finishing. Okay. So, the advantages: affordable for the job shop and production shops, reduces and or eliminates the skilled hand finishing operations, delivers repeatable uniform results every time. That means that if at all to be finished this type of blind surfaces for very good applications or high tech applications, you require the skilled labor. If at all you want to hire a skilled labor, the cost or in terms of the salary for the skilled labor will goes up. So, if you can automate the system using orbital abrasive flow finishing process, then you can finish this type of surfaces easily, and the production cost of these particular components will be always less. Okay. So, that is why this will be a good alternative to the skilled labor, and you can sell the products at minimal cost also, and the production rate also goes up. You can sell this particular product at a competitive price in the market. Possible input parameters of abrasive flow finishing process. Whenever in the slides I am talking about abrasive flow finishing process, that means by default I am explaining about two-way abrasive flow finishing process. Kindly all the people who are watching the video should note it down or should understand that I am clearly talking about the two-way abrasive flow finishing process, because the physics of explanation will be easier for two-way abrasive flow finishing process rather than one-way or unidirectional abrasive flow finishing process and orbital abrasive flow finishing process. That is why we always explain the finishing mechanism or the other things whatever I am going to explain will be corresponding to two-way abrasive flow finishing process. So, the workpiece parameters, initial surface roughness. Initial surface roughness is very important input parameter, because you cannot get a nano surface roughness if your surface roughness is 100 microns or 200 microns. For example, if you have developed a hole using EDM process with carbon based dielectric fluid, it is damn difficult to finish into the nano. So, what you have to do is your initial surface should be like 1 micron or less than 1 micron, then you can get the nano surface. So, that means that initial surface and initial surface texture and initial surface morphology, initial surface metallurgy will always plays a crucial role in abrasive flow finishing process to achieve the nano surface roughness. Passage geometry, if the passage geometry is too narrow, then the forces experienced for the same extrusion pressure will be very high, and it will you get the surface finish that is required in few cycles only. If the passage geometry is big, then you need more and more number of cycles. Passage area, so geometry and passage area, cross sectional area also play a major role, because if you have sharp edges like a square or something, then there will be your medium may not reach to those surfaces. Passage length, as I said, geometry covers passage area and passage length. So, the length if it is too high, there will be always problem of aspect ratio. If your aspect ratio is very high, that means there will be a pressure drop at the center of the workpiece region. So, you should go for the advanced mediums, and there are some of the advanced mediums that can overtake this type of high aspect ratio holes to be finished. So, material type, if the material is ductile, material removal will be very good. If the material is too hard, it will take more and more number of abrasive cycles. Okay. So, if the hardness is more, you have to go for high hard abrasive particles, and you can get the surface roughness as per your requirement. If you see the medium characteristics, media viscosity will play a major role, because the viscosity is high, that means that medium flow will reduce, but the thing is that it will try to remove the as much material as possible. Okay. So, percentage of abrasive concentration, the abrasive concentration is very high. If the abrasive concentration is high, that means that number of abrasive particles taking part in the finishing per unit time will increase. So, the material removal always increases. So, medium modulus of elasticity and medium density, these are all also will improve the abrasive action. At the same time, abrasive grain size, if the abrasive grain size increases, what will happen? The indentation will increase. Okay. If this is the abrasive size and this is abrasive size, what will happen is, for the same extrusion pressure and other things, the indentation created by the higher abrasive particle will be more. So, the material removal will be more. Abrasive type is, if you are going to have harder and harder abrasive particles, Like in one case you are going to use Al2O3, in another case you are going to use diamond. What will happen is the diamond will give you more material removal as well as better surface finish compared to alumina. So, abrasive hardness and shape, because abrasive hardness is a function of its abrasive type, because Al2O3 hardness is less compared to the diamond, and abrasive shapes, normally abrasive shapes are completely random. No two abrasive particles will be similar in looking. So, machining parameters are the finishing parameters. If you see, the most important one will be extrusion pressure. If you are going to increase the extrusion pressure, what you are going to experience is your radial force and axial forces will increase, at the same time axial velocity also increases, because of which what will happen, the finishing action will takes place, but up to certain limit. If you are going to increase beyond certain limit, what will happen, it not only shears the peaks, but also it creates its own scratch marks. Number of cycles, you require to optimize the number of cycles for each and every material with respect to the input conditions like initial surface roughness, type of workpiece material, type of abrasive material, and other input parameters you have to fix. Then extrusion pressure and all those things you have to fix. Then you have to optimize the number of cycles for each and every material combinations. The number of cycles will be different. Media entry profile to the workpiece, cutting forces, this type of things you can measure. Media flow speed, that means that how you can improve the flow speed and other things. Flow speed always will be function of your medium composition and extrusion pressure. If your medium is too low viscous and pressure is high, that means that medium flow speed is very high. Vice versa also, if the extrusion pressure is low, at the same time if the medium viscosity is very high, then the medium flow speed will be very less. Material removal rate you can use as a output response, and percentage reduction area, that means that if you could realize this is my fixture and this is my workpiece, and normally tapering will be given so that the medium entry will be smooth enough. That is why always the tapering will be given before the workpiece starts. Okay. So, what I mean to say that area reduction is the diameter of the workpiece to the diameter of the medium cylinder. This is the medium cylinder diameter, capital D, this small d will be the diameter of this one. Area reduction normally will be with respect to workpiece and the medium cylinder. Okay. If your medium cylinder is too big, normally what will happen, you require very few number of cycles. Possible output responses, normally the surface finish, axial and radial forces. Normally if you want to see the surface finish measurement, you can see in most of the papers, because abrasive flow finishing process is basically a finishing process. So, radial forces and axial forces, these are all you can see in only few papers, like Professor Gorana's paper you can see, but it is very difficult to measure the forces in abrasive flow finishing process, because in case of two-way abrasive flow finishing process I am talking about, in that circumstances you have to go for ring type of dynamometers. Okay. Or you can also go for acoustic emission based measurements and other things. Professor Williams and Rheological also measured using online monitoring, has done using acoustic emission sensors. At the same time, Professor Gorana and Professor V.K. Jain have done the force measurement with respect to ring type dynamometer and other things. Okay. Material removal rate, how much material is removed. This is the least bothered, because abrasive flow finishing process is about the surface finish that you are getting, whether you have achieved a nano surface finish or not, that is the question mark as per the current trend is concerned. But material removal rate also is one of the input parameters if at all you are going for the deburring application. So, out of roundness, normally out of roundness, if you see the, if at all you want to improve the out of roundness for a or cylindricity and other things, this can also be one of the input parameters, and you can improve the out of roundness by reducing or by shearing of the surface peaks. Load bearing area capacity, normally if at all you are going to reduce the surface roughness, obviously the load bearing area will improve. So, compressive residual stresses can be incorporated on this particular part, so that you can use in practical application and other things. So, we move on to the effect of one of the medium parameters, that is called plasticizer. We have taken here aluminum alloy, silicon carbide metal matrix composite. One is a purely aluminum alloy, second one is 10% SiC, third one is 15% SiC. So, do not bother about all these things. If you see the finishing mechanism with respect to plasticizers, you can consider any one curve, because we are interested to know about plasticizer. If you are going to increase from 2.5 to 17.5, the change in roughness is nothing but delta RA is nothing but RA initial minus RA final, that is initial roughness minus final roughness. Okay. If it is maximum, that means that the finishing is improved a lot. Okay. So, as you increase the plasticizer content, what is happening here is the medium gets better flowability and abrasion and other things. That is why as you move on from 2.5 towards 10, the medium gets better flowability and abrasion. As you move again from 10 to 17.5, what is you are going to see is it is decreasing. If you take three conditions, one is the initial condition, another one is the final condition and the middle condition. What it is going to do is, if you are going to have too less plasticizer, that means that your polymers are dominating. Normally polymers are dominating by elastic characteristics. If it is elastic characteristics are more, what will happen? Your radial force will be very high. If the radial force is very high, what will happen? It will indent more rather than the shearing. That is why the change in roughness is less. If the same thing happens in the on the other side, the same, if you are going to see here at 17.5, you will have ample or the more amount of plasticizer, softeners and other things are there. So, your medium is so low viscous, it will simply flow on top of it. As you can see, this is the grinding marks and the medium just flowing on top of it rather than shearing and other things. That is why you can see dominating lines here and very, very small marks of abrasive flow finishing are there here. Okay. So, this flowing, instead of abrading the surface, it just simply flows because you have too much amount of this particular plasticizers. Okay. So, if you are going to have the optimum amount, what is going to happen here is that you will get better flowability, better abrasion and other things. That is why you will get optimum amount of radial force, optimum amount of axial force and axial velocity, for which the shearing action will be good and change in roughness will be good. So, change in roughness with respect to extrusion pressure, if the extrusion pressure is too low, what is going to happen is the medium starts shearing. If you are going to have higher pressure, what is going to happen is it not only shears the workpiece, but also creates indentation, because if you are going to increase the extrusion pressure, what is going to happen is the radial force will increase. If you see the research papers, what they clearly conveyed is at higher extrusion pressure, the force ratio will be high. The force ratio means the FR to FA ratio. That means that your radial force will be dominating compared to your axial force. In that circumstances, the indentation will be high because your radial force is high. So, the indents will be generated on the workpiece surface. If you have optimum amount, normally what you are going to get is good abrasion because of low amount of indentation as well as proper shearing also, because of which what you are going to achieve is good change in roughness. So, medium and its rheology plays a major role, that is what I was telling you. So, medium has patented by few of the researchers across the globe, and our group also done the patent composition. So, some of the ingredients, all the ingredients which we cannot give. So, one of the things are base polymers, rheological additives like softeners, hardeners, plasticizers, antifungal agents, antibacterial agents and many more. So, abrasive particles and other things. So, basic properties of the medium as discussed, that is self deformability, better abrasion and better flowability. These are the minimum requirements for the medium so that it can be used in the abrasive flow finishing process. But this medium behaves uniquely. So, what is, if at all, if you make a sphere and put on a plate or a flat surface, what will happen is after some time it will become flat at the bottom. Okay. That means that because of the atmospheric pressure conditions, it is becoming that it is self deforming because of the atmospheric pressures, that is called self deformation. Okay. So, it is flows like a fluid. Whenever you put like this for long time, what will happen? It will become a flat and start flowing. Okay. Elastic behavior, or if you make a sphere and just hit with certain height, what will happen? The abrasive medium sphere tries to jump. Okay. The third one is, if you take it into a hand and if you just pull it from your two hands, what will happen? It is slowly deforms. If you are going to pull it very fast at a higher shear rates, it will break like a plastic material. So, the signs and deformation is unique here, because in one condition it is flowing, in second condition it is behaving like a elastic ball, in the third condition it is behaving like a plastic material. So, the flow properties as well as the deformation properties are completely unique. That is why this material has to be understood from the flow and deformation studies. The science of flow and deformation is nothing but rheology. Okay. So, the rheology can be understood for this particular medium by steady state rheology as well as dynamic rheology. Steady state rheology is nothing but with respect to time, we are not going to study in this. Steady state rheology don't deal with respect to time. So, flow test as well as creep recovery test and other things can be studied in the steady state rheology. At the same time, the frequency sweep, amplitude sweep and other things are studied in the dynamic rheology. If you see the schematic of the antenna power rheometer or parallel plate rheometers, you have a fixed plate here. This is the red one is a fixed plate and a rotatable plate is there on the top, and in between you have the medium. The red one which I have drawn is a medium. So, whenever you give the top plate a rotary motion, so it will shear from the periphery of the medium. You can have always a temperature controlling unit, so that if at all you want to check with respect to different temperatures and other things, also you can check. So, shear rate measurements. The first and foremost thing that you want to measure is the flowing ability of a medium. So, if at all I want to understand the apparent viscosity or the shear viscosity or the shear stress of a medium, I should know what is the shear rate at which I want to measure. For that purpose, one has to go for capillary rheometer. This capillary rheometer the medium, normally your L by D of this capillary should be greater than 18. Okay, you can study the rheology basics wherein this particular capillary rheometer and the parallel plate rheometer and other things will be given. Okay, so we have used the abrasive flow finishing setup itself because we have to understand what are the shear rates that the abrasive flow finishing process is experiencing. For that purpose, what we have done is we have placed the medium in a top medium cylinder and we have put a capillary to it and we have applied the extrusion pressure that normally we apply in the abrasive flow finishing process, so that we can collect the material and shear rate can be calculated by measuring the flow rate as well as we know the radius of the capillary and other things. From here we can calculate the shear rates. So, the plasticizer content and extrusion pressures, we have used the plasticizer content whatever we are using in a practical condition of the finishing, at the same time extrusion pressures also. Now, we calculated and plot the graph and you can see the shear rates ranging from 0.04 to 0.1. Okay, that means that my abrasive flow finishing process operates in this particular range. Now, once I know the input range of this one, then I can go for the various rheological properties. Okay. So, as you can see here, as the plasticizer content increases, what will happen? The medium viscosity will go down. The flowability of the medium will increase. That is why the curves are trending in an increasing trend with respect to the weight percentage of the plasticizer. At the same time, if you see here, if you are going to increase the extrusion pressure, what you are going to experience is that medium flow rate will be increased because you are putting more and more pressure on the medium. So, both the conditions are kept in this particular thing and we have measured the shear rates. Once you measure the shear rates, now you have to give the shear rates to the rheometer, where you can measure using a parallel plate rheometry. So, you can see this is the Anton-Par MCR 301 rheometer, and where you can see this is the bottom plate and this is the top plate or the tool master, and in between you are going to keep the medium. Okay. So, your bottom is fixed and the top will rotate. Whenever you are talking about the shear rate, that means that as you increase the shear rate means tool master will rotate at faster rate. Okay. So, if you see the analysis, the shear rate, as the shear rate increases, means what is going to happen here is the abrasive medium will experience more rotational effect from the tool master. If you are going to increase the shear rate, that means if you see any curve, what is happening is if you are going to have the initial, when the shear rate is low, that means that your top rotating place is rotating at slower speeds, because of which what will happen is your polymer molecular chains climbs one over each other and resist the flow. Gradually the viscosity of the fluid will increase because unity of the polymer chains along with the other ingredients and the abrasive particles will increase. But any polymer chain or any material have their own strength, beyond which it starts breaking and it align in the direction of the motion of the top plate. So, that is why in the section 1 it is increasing because of the unity of the polymer chains. In the other part, what it is going to see is that it is shearing, the polymer chains broke and align along the direction of the tool master. So, the downward trend is observed. Okay. These are the labeling is given for the plasticizer. Okay. So, if you are going to see the plasticizer, as you increase the plasticizer content, what is going to happen is the viscosity will reduce. That is what you can clearly see. How it will reduce? If you are not going to have any plasticizer, then the viscosity of the fluid is very high. If you are going to impart the plasticizer, normally polymer is high molecular weight material, plasticizer is low molecular weight material. When you try to blend these two, what will happen is low molecular weight material, that is plasticizer, softeners, this will go and sit in between the high molecular weight materials and try to kick off. That means that the distance between intermolecular chains of, or the intermolecular distance between two polymer molecular chains will increase. That means that intermolecular force of attraction between two chains will reduce. That is why the viscosity will reduce. That means that you are going to impart viscous nature, because the plasticizer, softeners, all these rheological additives are dominating viscous characteristics, and the base polymers are dominating in elastic characteristics and partial viscous nature. That is why the viscosity of the medium will reduce. Normally, shear stress is required to measure the viscous and elastic components. Okay. Normally, I want to understand what is the viscous component and elastic component from this particular graph. Okay. I will go back to the previous slide to measure the linear viscoelastic region. Before that, you should understand why I require to measure the linear viscoelastic region. Okay. So, in this one, this is the creep recovery test. What is happening is, suddenly in this one, what you are going to put is, you are going to put sudden shear stress, then you are holding for some time, and you will observe the creep compliance. Okay. Compliance is nothing but inverse of your modulus. That means that stress by strain is modulus. If you are going to reverse it, strain by stress is nothing but your compliance. Okay. So, creep means sudden load you are applying and you are holding for some time and you are observing the strain. Okay. Since your stress is, or the load is constant, so the strain will continuously change with respect to time, and you will want to observe the strain. Okay. That is what is done in this particular. The basic problem here in this curve is that how much load one has to apply. Okay. For that purpose, the people have to do the shear stress or the shear sweep curve. So, in this one, I am going to increase the shear stress and I am observing the storage modulus. As I increase the shear stress, there is no change in the storage modulus initially, but later on it is decreasing. That means that even though I am changing the shear stress up to certain value, up to this particular value, there is no change. That means that my polymer molecules are at original state. Okay. So, if I can give any particular value of stress in this one and I can measure the viscous and elastic component in the next slide, that I am going to get original value of viscous and elastic component. Assume that if at all I am going to give this particular region value, what I am going to get here, the polymer molecules are damaged or polymer molecule chains are broken. So, I cannot give. So, if I can give the linear viscoelastic region values, that means that my polymer molecules are at original state and I can measure the original value of viscous and elastic nature. For that purpose, I have given here 100 Pascal, which is taken from the previous slide, which is in the linear viscoelastic region, and I am observing the viscous and elastic component. A to B is viscoelastic nature, B to C is elastic component. Once you know A to B is viscoelastic nature and B to C is only elastic nature, if you can subtract it, you will going to get the viscous nature. Okay. This is about your elastic component and this is about your viscoelastic component. This is your viscoelastic component and this is your elastic component. So, you can get the viscous component. from this particular curve. If you know the viscous component, if you know the elastic component, then it will be nice to understand about how much is the radial force, because radial force is a function of your elastic component, how much will be axial force and axial velocity. These things you can understand easily. So, similarly you can do the strain sweep test also. From the strain sweep test you can use that linear viscoelastic region in stress relaxation. Always stress relaxation should be faster, because the medium has to pass through your narrow region and it will go to medium. Because of the self deformation, if it has to relax, and self deformation will be fast if your relaxing ability of the medium is very high. That is why you should always go for good relaxation. Since these curves are following log, do not go by the bottom curve has the highest or the top one has the highest or something. Okay. So, the best one normally will be the 10. So, you can see the curves and you can understand. So, the complex viscosity of the medium, if you are going to increase the frequency with respect to the time, normally this comes under the dynamic. So, where the complex viscosity normally can be measured, or you can also measure storage modulus, loss modulus and tan delta and other things also can be measured. If you are going to increase the frequency, normally the viscosity will gradually decreases, because the polymer chains will break and the viscosity will gradually decreases. If you see the effect of rheology on the finishing of the medium, if you are going to measure your viscous component plus elastic component considered to be 100% in a viscoelastic medium, if you are going to have 35% of viscous component, that means that here, so 65% will be your elastic component. That means that elastic component is too high, because of which it is not only shearing the peaks, but also it is creating its own scratch marks. That is why the change in roughness is less. If you see at 55, normally what you are going to experience is a very good surface. This is because you have sufficient amount of elastic component, sufficient amount of viscous component, and you are going to abrade uniformly across the surface with a better flowability, better abradability. That is why you are going to get the better surface. That is why you are going to get better surface finish. So, the other variable in the medium rheology is nothing but temperature. Okay. So, temperature, what you are going to see here is, if the medium temperature increases, the medium viscosity will gradually decreases, because if you are going to increase the temperature, the medium polymer molecules gains energy and try to move apart. When the molecules are moving apart, the distance between two polymer molecular chains will increase. That means that polymer molecular attraction forces between two molecular chains will reduce. That is why always the viscosity will reduce. The advantage of this one is, if the viscosity is high, what will happen? You can finish the bigger holes. If the viscosity is low, then you can go for smaller also. Assume that I am going to have only one medium. If at all, if my abrasive flow finishing process has a temperature controlling unit, you can play with the temperature and reduces the viscosity of the medium, and you can use for the small type of components or small geometrical features also can be finished. Okay. That is the beauty about the temperature dependent rheology of the medium also. Normally, if you see you can do for the micro applications, the finishing of micro holes that are on the fuel injector nozzles can be finished, and this is the recast layer. This recast layer can be removed and it can be finished. At the same time, deburring, I was talking about in some of the cases deburring and other things. Exclusively I kept this particular slide for for those people who couldn't understand what is a deburring operation. Whenever you do the drilling operation at the edge, at the bottom side, you get this type of burrs. This is nothing but a burr, and if you are going to remove it by the abrasive flow finishing medium with a low viscous medium, you will not only remove these burrs, but also you will get radiusing. Okay. So, two things one has to understand here is the finishing of the micro hole is done, at the same time deburring also done and radiusing also done. Okay. This is the most beautiful thing about the abrasive flow finishing process. So, you can see the surface roughness, as I said, initial surface roughness is always important to understand and to get the nano surface finish in the later cases. So, initial surface roughness is 900 nanometers and the final surface roughness is 70 nanometers, and the initial profile and the final profile, you can see the mirror image of the pen tip in the workpiece. Okay. So, this is how you are going to finish this particular components. So, the applications, finishing of extrusion dies, nozzle also can be done, valves of the aircraft, and it can remove the recast layers and other things that can be done. If you can see here, before and after, it is finished in a great level. At the same time, you can see head of the hip joint also can be finished. Okay. These are the things that can be done by the abrasive flow finishing. These are the extrusion dies. Various type of extrusion dies can be finished by the abrasive flow finishing process, and you can also do the finishing of multiple holes in a die also. Okay. That also is possible. So, this is what I am talking about, the recast layer. So, this is a laser beam machined surface. You can see the recast layer, that means in a laser beam machining, melting and evaporation is normal phenomena. If the material is not gone, or that means that if the material is unable to remove, or if by the virtue of the gases or atmospheric gases, or the normally some of the laser assisted machining processes or like air assistance will also be there. If the material is not removed, this will be stayed like a recast layer. Molten material will stay there in the form of a layer, that is called recast layer. As I said, casting means melting, then you just put into the mold. So, here there is no mold, but molten material will solidify again. That is why this also resembles like a casting technique. That is why the layer formed here is a recast layer. You can see here how the recast layer is there. If you are going to put this particular component in a practical application, it is going to fail as early as possible. For that purpose, you should always try to finish this surface, so that you will remove the recast layer and the life of the component will increase. You can also do for the filters and other things, and you can see how the holes are finished using abrasive medium here. So, the other advantages, surface finish you can get up to 50 nanometers, dimensional tolerances you can get up to 0.005 mm. The good finishing and the difficult to finish internal shapes also can be done. Nanometrical surface finish can be achieved. Complex geometry shapes can be finished, can be used, and deburr, polish, radius that we have seen in the previous slides. For removing the recast layers that are formed in laser beam machining and electric discharge machining and other processes can be done using the abrasive flow finishing process. So, for developing the compressive stresses, that is residual compressive stresses also can be developed, and process multiple passages in a single go also can be done. This is the advantages of this particular process. This process has limitation like low material removal rate. Production time is very high, because as you are going to increase the finishing time high, the viscosity of the medium will go down, and medium cost is very high. If you at all you want to go for the commercial medium, normally the medium is too expensive. So, the production cost of your finishing component will goes up. cannot control the abrading process during the finishing because the medium is a one, and along with the extrusion pressure will decide this one. It cannot correct some of the problems like taper problems, out of roundness, bell mouth, barrel and boring marks and other things cannot be done by this particular process. This particular process only can finish the surface, but not change the shapes, okay, because the material removal in this abrasive flow finishing process is too less. So, summary of this particular class, we have seen the introduction to abrasive flow finishing, various elements of abrasive flow finishing, various types of abrasive flow finishing, input parameters and output responses, medium rheology and its effects on finishing, advantages and applications of abrasive flow finishing process. Effectively, we have seen about the conventional abrasive flow finishing process, and we move on. If time permits, we will see the advanced versions of abrasive flow finishing process like drill bit guided, spiral polishing, centrifugal force assisted abrasive flow machining process and other things also in upcoming classes, subjected to if the time permits. Okay. Thank you for your kind attention for this particular class, and I am very thankful for various researchers for their figures and other things in the area of abrasive flow finishing. Thank you.